Hi, everyone. We'll start in around 9 minutes. So I opened the room a little bit earlier to give people time to arrive. Thank you for coming. Hi, Hannah. Nice to see you here. If you want to come up and speak later, you're welcome to. Thank you. Hey, everyone. Thank you so much for coming. We'll start in around 8 minutes. So if you want to come up here, yeah, please raise your hand and you will have the opportunity to talk with our guest speaker. Hi, Tuan. How are you doing?
I'm good. How are you?
Good too. Thank you so much. I'm excited about this room, so I'm happy.
Yeah. I look forward to hearing the speaker. Yeah.
Hi everyone, thank you so much for coming. We'll start in around 4 minutes. So yeah, please stay tuned and thank you again. Hey Dennis, how are you? Thanks for coming.
Hi, Katarina. This should be exciting. I'm a space nerd.
Yep. I hope everyone is well on this Thursday, and we'll start in 2 to 3 minutes. Tim, he's on his way. He just wrote me an email, so stay tuned. Hey everyone, thank you so much for coming. Hi Gilbert. We will start shortly. Um,
Hello,
so
hello everybody.
hi Gilbert, how are you doing?
I'm good, good. How are you?
Good, thank you. We will start soon. Um, Waiting on Tim. So yeah, he wrote me an email, so he should be here
Tim just
any.
popped in. He might
Oh,
need a
there
moment
you
to
are.
gather himself.
Hi. Sorry. How are you, Tim? Thank you so much for coming. Can you?
Yes. Hello. Yeah. Hi. Hi. I couldn't work out how to unmute myself. Um. Yeah. Hi. Thanks for having me.
Yeah. Thank you. Don't worry. It's your first. Welcome to having your first room on Clubhouse. So congratulations. And
Yeah. This is very exciting.
yeah, so welcome everyone to the Science Society, and we are very honored to have today on really interesting research presented by our guest speaker, Dr. Tim Cunningham, and let me introduce him to you. So, Dr. Tim Cunningham did his master's in science in physics at the King's College London, and he was a research assistant at the University of California, Santa Barbara, and later and until now he is a postdoctoral research fellow at the University of Warwick, and he is in the field of astronomy and astrophysics, utilizing multi-dimensional radiation hydrodynamics to study convection in degenerate stars and white dwarf populations. He's very experienced at using spectroscopy. I don't know what's wrong with me today, and photometric expertise. And we are very honored to have you here, Tim. Thank you so much, and the stage is yours.
Great, thank you so much for that introduction, Katerina. Hi everyone. Thanks for having me. It's very exciting to be here. I just wanted to check if people have access to the paper. I don't know how easy it is for you guys to give me feedback.
It's if you look above our heads, basically, there is a link posted to the archive version. I posted that one so everyone can look at it.
Okay, so we'll just go with the archive version. Okay, cool. I loaded both versions just in case. But yeah, in that case, I'll just refer to the archive version with page numbers. I think that that version should have 53 pages if we're singing from the same song sheet. So I'll refer to that throughout. As Katerina says, I just see a message there. We have access. Cool. All right. Thanks, Victoria, for letting me know. As Katerina says, my expertise are in multidimensional simulations of stellar atmospheres. Primarily, I'm interested in convection in the atmosphere of white dwarf stars. That's where I started my PhD research. And the recent detection of X-rays was a proposal I put forward to test models of convection, actually, in the atmospheres of white dwarfs. And I'll give you a little bit of detail around that. But I know we're quite interdisciplinary audience, so I thought I'll just give us a bit of context for what this paper set out to achieve. And also, I'd like to say, feel free to jump in at any moment with questions. I'll try and keep my eye on the chat, but feel free to just interrupt me if you have questions at any point. So, a white dwarf is the end stage of life for 98% of stars in the universe, including our own star, the sun. Any star that is born with less than about 8 solar masses will evolve into a white dwarf. And we now know of, from the Gaia space satellite, we now have a sample of 250,000 white dwarfs in the local galaxy. On average, each of these white dwarf progenitors, so each of these main sequence stars, on average, every other one hosts an exoplanet. So on average, 50% of main sequence stars host an exoplanet. And obviously our sun hosts many more than just the half a planet. And it's evolved into a huge field of study as to what happens to planetary systems around main sequence stars as that star evolves. So in a few billion years, when our sun evolves, it will strip off about half of its mass, and it will leave behind a white dwarf. The close-in planets are going to be engulfed. Earth may or may not be engulfed, and any planets further out than Earth will not be engulfed, but their orbits will move out as the mass of the star decreases. And so this event will induce lots of dynamical instabilities in the planetary system, and that can lead to asteroids, moons, planets being scattered towards the remaining white dwarf. And we see indirect evidence of this in the form of metal lines. So, as Katerina said in the introduction, we work with spectroscopy, and this technique gives us the wavelength-dependent emission from a star. And in general, when you look at a white dwarf, the spectrum of a white dwarf, you expect to only see evidence of hydrogen, and in some cases, evidence of helium. But in about 25 to 50% of stars, or 25 to 50% of white dwarfs, we see heavy elements. So things like calcium, magnesium, iron, silicon, aluminium, carbon, lots of elements which we know to be in planets, including our own. Now, the reason that this is the reason this stood out as being something that was surprising is that white dwarfs are extremely dense, and so you expect these heavy elements to sink out of the visible layers on very short timescales. The fact that we see these heavy elements in the atmosphere suggests that this material is falling onto the surface, so it's being constantly replenished, and that paradigm is supported further by the presence of debris disks around white dwarfs. And I think about 6%, 5 or 6% of white dwarfs are observed to have a debris disk, a circumstellar disk of material orbiting them, and that is inferred from infrared observations. So over the last few decades, this field of metal pollution in white dwarfs as a signature of evolved planetary systems has evolved into a very active field. And there's also been detections of transits of solid bodies in front of white dwarfs, as well as the accretion of a giant planet just published 2 years ago. So there's been lots and lots of indirect evidence that after the formation of a white dwarfs accrete the remnants of old planetary systems. But up until the research that we published in this paper, all of that evidence was indirect, and it was long predicted that accretion of material should produce X-ray emission. This is something that has been observed in many different types of objects, including white dwarfs accreting from main sequence stars, or neutron stars which are accreting from main sequence stars. In both of those cases, the accretion rates are extremely high, and the X-ray production is very high. So the X-ray flux is much higher. In the case of metal polluted white dwarfs, the accretion rates are many orders of magnitude lower than these other astrophysical objects, about 8 orders of magnitude or more lower. That makes it extremely difficult to detect these things. And it required a very deep pointing. And that's what we did with this observation. So we pointed the Chandra X-ray Observatory at one of the best studied white dwarfs, G29-38, in search of X-rays. So we knew from the spectroscopic method, so the measurement of metal abundances in the atmosphere coupled with models of the white dwarf atmosphere, we had an inferred accretion rate. So we had an idea about how much material was falling onto the surface of this star per second. That accretion rate was 10 to the 9 grams per second. That is about 8 orders of magnitude less than, say, a white dwarf accreting from a main sequence star. Based on that accretion rate, we predicted an X-ray flux and decided that an exposure of 115 kiloseconds, so that's something like 34 hours, with Chandra should be enough to detect this emission. In the end, we got 106 kilosecond exposure with Chandra, and we made a detection of a 5 to 5.5 sigma detection of X-rays from the expected position of our target. Now we've been able to do a lot of modeling on this observation, and the exciting thing is that this is the first direct evidence that white dwarfs are currently accreting. Oh, was that a quick? Okay, it's just someone coming in. But yeah, for anyone who's just joined, I said at the beginning, feel free to interrupt me at any point if you have any questions. So yeah, we've made the first direct, we've made an observation of X-rays from our G29-38, a metal polluted white dwarf, and this is the first direct evidence that white dwarfs are currently accreting. So if in the archive version, you can go to figure 1, and you can see the X-ray image on the left. So what you're seeing there is a pixelated image of from Chandra. In cyan are pixels which received 1 count in the total observation time, which was 106 kiloseconds, or 32 hours. In pink are pixels which received 2 photons. Now, something that was really quite necessary for this Chandra observation was its angular resolution. A different X-ray telescope, XMM Newton, had also been pointed at this object over 10 years ago. But the problem with XMM is that its angular resolution is not very good, or significantly worse than Chandra. So critical to this observation, you'll see that to the right of our source, which is shown in a green circle, is a much brighter object next to it. And in XMM observations, the 2 sources get blended, and you can't distinguish the much dimmer source. So yeah, our source is the one on the left in the green circle. On the right image, I'm showing a pan-stars image. So this is an optical imaging survey, which shows our target very brightly. Now that pan-stars image was taken 7 years before our observation. And that's why it's in a slightly different location on the image, because this object is relatively close to us at just about 50 light years. And it's moving relatively quickly across the sky. So just in those 7 years, it's moved something like 3 arc seconds across the sky. Now, one of the really exciting things about this observation is that all of the photons we detected are relatively soft. We've actually detected here the lowest accretion rate ever measured, and that was predicted to produce a very soft emission spectrum. So in figure 2, I'm showing the sky location of each of the photons that we detected with their energies in the shown in color. So all of the photons that we detected come with energies between 0.7 and 1.3 kiloelectron volts. Chandra is most sensitive above 1.3 kiloelectron volts. So the exciting thing about this is it sets an extremely robust upper limit on the emission spectrum. Because if the emission spectrum was any harder, so if it was emitting any harder X-rays, which is what it would do if, say, the accretion rate was higher, the plasma temperature was higher. Then we would have detected many more photons at higher energies. So this is really exciting because it confirms something known as the bombardment solution, which was, well, we discussed in the paper, but yeah, it confirms a prediction that was made in the 80s that at these really low accretion rates, we predict these really low temperature plasmas. And perhaps, yeah, I haven't really mentioned what's actually happening here. So as this rocky material is moving from a disk onto the star, so it's falling in, converting its gravitational potential energy and forming a plasma at the surface. So when these atoms slam into the surface, they will be shock heated, forming a plasma. That plasma, depending on its temperature, will cool predominantly via line emission. So this will be recombinations of ionized elements. And this will produce photons at specific energies. So another really cool thing that came out of this discovery is that probably one of those photons came from a magnesium atom. Yeah, perhaps I can skip ahead because it's, sorry, there's so many pages in this archive thing. But if you go to figure 4, extended data figure 4, it's on page 41 of the archive observation. You can see the photons that we detected in black in the bottom panel. So there are the energies between 0.8 and 1.3 kiloelectron volts. Now that photon at 1.3 kiloelectron volts, you can see I've plotted the line transitions for all of the elements that we suspect, or that we know from spectroscopic observations that this object has accreted. So we know that it's accreted because in the atmosphere of the white dwarf, we have observed oxygen, iron, magnesium, silicon. So that photon at 1.3 kiloelectron volts lines up very nicely with the expected transitions of magnesium in the same region. Same for the photons slightly lower energies of 0.9 kiloelectron volts, are most likely to have come from ion transitions. Now those elements will have been locked inside a planet or some planetary body, an asteroid or a moon, for billions of years potentially before the planet has come close enough to the white dwarf that it gets tidally disrupted. So it gets shredded by the tidal forces because it's got so close to the white dwarf. And then as that material has been ground down and landed on the surface, we're seeing those atoms that were locked inside some rocky material for billions of years, and producing an atomic transition and producing an X-ray that we've detected. So that's one of the main takeaways from this research. And yeah, if you now look at extended data figure 3, I'm showing the same observed photons on the bottom panel and the sensitivity of Chandra as a function of energy in the top panel. So that illustrates the point I made earlier, that Chandra is most sensitive at these harder energies or higher energies. So if we had a spectrum that was significantly hotter, then we would have detected many more photons above, say, 2 kiloelectron volts. So the absence of photons there really makes it extremely convincing that we've detected a very soft source of X-rays, meaning that the plasma from which they were emitted was relatively cool. But we're still talking millions of Kelvin here. Okay. So the next exciting thing, now that we've derived the so now we've constrained to some degree the plasma temperature, we can go a step further and estimate the accretion rate that is producing that emission. So I'm going to jump back. If we go back now to figure 3 of the main article. So in the archive version, that's on page 18. And in case anyone's looking at the Nature article, that's on the 3rd page. But yeah, figure 3 in both versions. So here what I've plotted is the accretion rate derived from the X-ray observations using a few different sets of abundances. So we know from spectroscopic observations the abundance of elements in the atmosphere of the white dwarf. And so that abundance profile I've labeled photospheric. So that's the abundances that were observed at the photosphere of the white dwarf. For anyone not familiar with the term photosphere, that's just the point from which 2/3 of photons are able to escape the star. And in the case of a white dwarf, that's extremely near the surface. So something like 10 to the minus 18 of the star. Yeah, you're in the sort of 10 to the minus 18th layer of the star, if you like, in mass. Another abundance profile which we tested was bulk Earth. The reason for using something other than what's been observed in the photosphere is that there may be elements that we're not sensitive to via the spectroscopic method, because the sensitivity to various elements is a function of the white dwarf temperature and the wavelength range in which you look. And we know that we're accreting the remnants of an evolved planetary system. And so bulk Earth probably gives us potentially gives us a better constraint on elements that we're not sensitive to. So the accretion rates for those two sets of abundances are shown in those blue bands. So you can see that we're not very sensitive to these different abundance profiles, and that we derive an accretion rate of around 1.5 times 10 to the 9 grams per second. The really remarkable thing here is that this agrees extremely well with what was predicted from the spectroscopic method. So for anyone who's just joined, the spectroscopic method that I mentioned is where we take a spectrum of the white dwarf, derive metal abundances, couple the observed metal abundances with a model of the white dwarf atmosphere, so that will be a numerical model, and infer from that how quickly those metals must be sinking from the atmosphere out of the visible layers. And from that, you can derive an inferred accretion flux. And that's how we've studied these systems for a few decades at this point. What we have here shown in blue is the very first accretion rate derived from X-ray observations, and it's the first independent constraint on the accretion rate at an object like this. We now know of over 1,000 metal polluted white dwarfs, and the local sample of white dwarfs numbers, well, we know of 250,000 white dwarfs. So there are many of these objects out there. So this is a very exciting step towards building a really solid theoretical and observational system by which we can study these objects.
Do these accretion rates
question?
match simulations?
Yeah. So in the simulations, there's two sets of models that I've included here. There's the old school, which is in pink, labeled no overshoot. And then there's the new school, which is labeled overshoot. Now these, I see. So, yeah, so simulations. Yeah, so you can, well, in some ways this is, so I'll back up. So the solid lines here, the no overshoot and overshoot, these are models that do know about the calcium abundance for this object, but the sinking times of each element, so the calcium sinking time, is driven by numerical models. And the pink and the green either include or don't include convective overshoot. So convective overshoot is a boundary phenomena which occurs everywhere that you have convection, and it effectively extends your convection zone compared to the naive assumption. So a convection zone is a fairly complex place, it turns out, and you have a region where you can drive instabilities, and for over a century, so the first convective models were laid out by Prandtl in 1925, or at least the ones that were used in stellar evolution models. So they capture fairly well the region that you have numeric convective instabilities emerging. But it turns out from multidimensional radiation hydrodynamic simulations that the convective overshoot can actually mix a significant amount of material outside of these regions. And so that's the difference between the pink and the green lines, is whether you do or don't include this convective overshoot, this additional mixing. Now, in terms of, I suspect your question, I missed who asked the question. Was it Chris?
How does it conform to simulations?
Yeah, so there's a real dearth of simulations of accretion rates onto white dwarfs. And I think that this study is going to precipitate, well, I hope it precipitates a lot of interest and a lot more work in that department. So yeah, we don't have, there is a real dearth, actually. There's a real gap in the market for some simulations of accretion rates onto white dwarfs from planetary debris disks. And because this is the first independent constraint on the accretion rate, it's quite exciting to think what can be done in the next few years in that department.
I've been looking at editing limits for micro black holes for how fast they on kind of the opposite side of the spectrum. From, if you got white dwarfs being massive objects versus very, very small ones. But it seems that there's some differing perspectives from the simulations of how fast material can actually accrete. Like, can a micro black hole actually eat matter at a certain rate, or is that something that you have to be a certain minimum size to do so? I was wondering if you might have any thoughts on that.
Interesting. Yeah. I guess in the case of black holes, you've got immense radiation, which would counteract your ability to accrete at high rates. Yeah, I don't know. That's an interesting point. Yeah, it's a good question. I don't have a very well formed answer for you. I'd have to probably give it a bit more thought, I think.
It's been fun crash coursing on accretion disk physics, though. There's some really cool things kicking in there, especially when you start moving to cares and start modeling like the space-time distortions. It's just insane. But what's really crazy about it is that it's very difficult to observe the exact effects, so we have to work with secondary data. Being able to calibrate simulations with other heavy gravity objects from white dwarfs directly is extraordinarily exciting.
Great. Well, if you wouldn't mind sending me a few references, I'd be very happy to see what you've dug up. Great. Thanks, Chris. So yeah, we've really been, this field's really been driven very observationally. Well, most of the modeling that's been done has been in the white dwarf atmosphere, and there are a lot of people doing. There are n-body disk simulations which are happening, but mostly in this field, there's been a lot of focus on how do you get material near the white dwarf, like near enough to form a disk in the first place. But I think that there is definitely a gap in the market for our predicted expectations for at what rate material can move from the disk to the white dwarf. And I predict that this discovery will precipitate some efforts in that department.
Can you get into the next Interstellar movie so you can get more funding for the visualization research?
Yeah, if you know anyone, put them in touch. I'd love it. But this discovery definitely touches something that is it's close to home in the sense that this is the likely fate of our own solar system. And yeah, we're by studying these metal polluted white dwarfs, we're learning what's going to happen to our own solar system, as well as lots of the other. There are now, I think, over 4,000 exoplanets that have been discovered around main sequence stars. So we're also learning what's going to happen to them. And looking at the bigger picture, tying observations like this and this whole field of metal polluted white dwarfs, tying that together with exoplanets around main sequence stars, is going to paint an extremely detailed picture of the evolution of a planetary system from formation to being fully developed to its ultimate fate.
Are there certain sensors or astronomical devices that would make your detection sensors or the sorts of science you want to do more easy to do, or is there certain wavelengths that are very useful to look at?
Yeah, so there are other X-ray observatories that are actually more sensitive than Chandra. XMM is one of those, which is currently active. And I did mention that XMM had already given this object an observation, but because of its angular resolution, it was unable to separate this object from a much brighter source nearby. And that's where Chandra is really advantageous. But XMM already offers greater sensitivity. So that's one very exciting prospect for the future. And finding more of these objects is XMM. There's also Athena, which is an X-ray telescope that's coming in the next few years, I think by like 2030 or 34 or so. There's eRosita as well. So there's lots of exciting things happening with X-ray observatories that are really going to be great for finding more of these objects. One wavelength regime that would really help us here would be the extreme ultraviolet. And the reason for that is that we have an emission spectrum which is very soft. And I said before, it's super exciting that we can say that it's very soft because we didn't see this harder X-ray emission. The problem is we don't really know how soft it goes. And that's the major source of uncertainty, really, in our results. And unfortunately, there is no instrument that's optimized to observe in the extreme ultraviolet. So this is the region of wavelength space between the ultraviolet and the X-ray.
Isn't that filtered by atmosphere?
So in the UV...
Is that filtered by atmosphere?
Like the Earth's atmosphere. Yeah, you wouldn't be able to do UV or X-ray from Earth. So we can only depend on space-based instruments. At the moment, we have the Hubble Space Telescope, which can observe in the ultraviolet. There is no follow-up UV mission that's going to replace Hubble that's like on the horizon, so that's a real issue. And there's also no instrument that can currently or even planned observe in the extreme ultraviolet. So that would be a really nice wavelength regime to be able to probe. But one of the issues with the extreme ultraviolet is that the interstellar absorption of extreme ultraviolet, so there's not Earth's atmosphere, but just interstellar medium, is a major limiting factor. The absorption there is extremely high in the extreme ultraviolet, and so building a mission there is very expensive. So yeah, at the moment, X-rays is where it's at for this kind of stuff, because there are at least 2 or 3 other missions that are either currently active or soon to be active, and I'm optimistic we'll find many more of these objects.
Actually, can you speak a bit more about the different sources of uncertainty? And yeah, because I see that the quote uncertainty is quite high. Is it typical of this kind of measurement? And what are the plan and also can you speak, explain a bit about the different sources of statistical and systematic uncertainties,
Yeah,
and then is there any plan to deal with them in future work or in future measurements?
yeah,
Thanks.
absolutely. Great question. Okay, so I've already said that the extreme ultraviolet provides the greatest source of uncertainty on our accretion rate. And if you look at extended data figure 6 and 5, you will see why. So in extended data figure 5, we have the best fit plasma spectrum based on the observed photons in the X-ray regime. So in extended data figure 5, so in the archive version, that's on page 42. You've got 3 bands labeled soft, medium, and hard. So they are standard Chandra science bands. All of our photons were detected in the soft and medium band. And we have a best fit spectrum based on the emission that we observed there. But that best fit spectrum extends down into the extreme ultraviolet. So that's the region below like 0.3 kiloelectron volts or so. And that's where we have no instrument that's capable of constraining what's happening there. And that would be the dream, but we don't have it. We're not going to have it. But based on how that spectrum behaves at these lower energies, that will affect the accretion rate. And so in extended data figure 6, we show 3 extrapolations. So we show an accretion rate derived in the observed bands in A and B. But then in panel C, we extrapolate, well, we integrate the best fit emission spectrum right the way down to the ultraviolet. And that massively increases the accretion rate. So really the accretion rate in figure 3 of the main paper that we were just looking at should be considered in some sense a lower limit. And instead the fact that we don't really have a good handle on what's happening to that really soft emission means that we have these really asymmetric error bars in the accretion rate, and have a huge uncertainty at the upper end of what the accretion rate is. Now, one of the solutions to this that we're currently working on is coupling our observation with UV observations from HST, and there we may be able to provide at least some constraints at the upper end, at the extremely soft end. So that's one thing that I'm currently working on to try
So
and
if I'm
improve
reading this
that.
right, it's 1,000 tons per second, give or take, for the accretion rate for like the lower end.
Sorry, 1,000 tons per second. Yeah, that no, it should be 1,000
Or
tons.
10 to the 9 grams.
Yeah, 10 to the 9 grams per second. Yeah.
Subtract 3 for
So is
each
that
jump.
1,000? Yeah. That sounds right. So so you can see that the 90% confidence interval at the upper confidence bound of 90% is up at almost 10 to the 11 grams per second. This observation does not rule out extremely large accretion rates, and I think that we can do better with what we've already got, as in not this observation, but coupling this observation with some UV observations. I think we can improve this. So that's exciting. So that's really the major source of uncertainty on the accretion rate. We did rule out, so that there is another possible source of uncertainty on the accretion rate, and that is that if this white dwarf was strongly magnetic, you may expect the material to be channeled onto a pole, and in so doing, it may have some additional cooling through cyclotron emission, which would be detectable at, well, maybe not detectable, but it would be emitted at radio wavelengths. So we provided a constraint on how much cooling we might expect from cyclotron emission, and it was really negligible. So really the main source of uncertainty is what's happening in this extreme ultraviolet regime. And the reason we can place such a tight constraint on the cyclotron emission cooling is that the 3 sigma upper limit on the magnetic field strength of this object is extremely low, something like 1.5 kilogauss. So this object has no detected magnetic field. So even if it has a magnetic field at the 3 sigma upper limit, it's unlikely to induce significant cyclotron emission cooling. So that's the main uncertainty on the accretion rate. Now, you also asked about some of the statistical uncertainties, and there are a few, or at least there's a few important things that one needs to constrain in these kinds of observations. So the first statistical significance that we're interested in is this an X-ray source? So is this a significant source of X-rays? And the answer is yes. By using Poisson statistics, you can convert your observed counts given a certain background into a source significance. So you can test a null hypothesis that what are the chance if there was no source there, what's the chance of receiving X number of photons for a given background. So that's how we derive whether we even have a significant source of X-rays. And we, depending on the aperture size, in Chandra, for such a soft source, it's recommended to use an aperture size of 0.5 arc seconds. So if we use the 0.5 arc seconds, we find that we have a source significance of 5.9 sigma. So we're confident that we have an X-ray source there. But the next important significance to probe is, okay, there is a source there, but how do we know it's our target? And how do we know it's not just some other X-ray source that happens to be exactly behind where we're looking, which is, of course, possible. And so to do that, we use two methods. One is a Monte Carlo approach. So we place 1 million apertures in the field in the observed image, and we say, what is the chance across the entire image of detecting a source as significant as the one that we have? And then you can derive a sky density of sources with similar brightness. And in so doing, we can rule out that we just have the chance alignment with some other astrophysical objects at a significance of 4.4 sigma. So that's why in the abstract we quote a detection of 4.4 sigma. The X-ray source is detected to maximum 5.9 sigma, but the probability of chance alignment we can rule out at 4.4 sigma. Then, in terms of the uncertainty on the count rate, we use a method put forth by Kraft, Burrows, and Nusek in 1991, which is very standard Bayesian analysis, or Bayesian provides a Bayesian constraint on source. The uncertainty on count rates for very low number statistics. So in X-ray and gamma ray astronomy, a handful of photons is not uncommon. So it's important to have robust statistical models that can deal with such small numbers, where uncertainties most certainly are not Gaussian. So I think that covers the dominant sources of uncertainty and the statistical methods we went through to analyze the observations. So, Swan, hope that answered your questions.
I have a
Yes, thank you. Yeah.
I have a very brief one. If Chandra is one of the main ways you're getting a lot of your sensor data, a lot of this was designed during eras of very expensive space launches where every gram counts. So they have to be very careful what science equipment they put on. It's very, very expensive to launch satellites. If we enter into an era where SpaceX is doing weekly launches of 100-ton masses to any point they want in the solar system, what would you do if you had 100 Chandras to play with? How much would this increase your science?
Yeah, good question. That is a good question.
They might be shitty versions because they were designed so quickly. Because it's like, oh crap, we got a launch capacity, use it.
I mean, 100 Chandras doesn't sound too bad to me. Yeah, just same again, please.
Just put a little more ultraviolet sensitivity on there, and you're good to go.
Yeah. Slightly softer Chandra would be nice. I mean, what is amazing about Chandra is its angular resolution. Although I've said this, that we've got lots of exciting X-ray missions coming up. None of them have the angular resolution of Chandra. So Chandra is fantastic, and 100 Chandras would be a real nice way forward, I think. But that's a good question. But
You get a lot of doctoral students for the lab.
Yep. One
you get
per
a Chandra. You get a Chandra. Everyone gets a Chandra.
Yeah. That sounds pretty good to me. I think I've said all I wanted to say about the paper. So, are there any other questions out there? I can see a kind of paper airplane. What does that mean? Is that messages? I see messages.
Yeah, exactly.
Okay, from.
Yep.
Okay, that's
There's also a tab for requests for new messages as well. It's useful for people sending links to each other and such.
Okay, cool. All right, thanks for that. Cool. I guess people will jump in if they have other questions. Oh, requests. Yeah, I see. Okay. No, this is a very exciting time for this kind of science. We're entering a wave of big data. We have like huge spectroscopic surveys which are just starting up now, and we're going to be able to detect and study these objects in unprecedented sample sizes. So
cool. Once you give the characterization data, you can have an AI filter that all out, which would mean that you could just get here are the prime candidates for whatever your research thing you're looking at. That is so cool.
Exactly. Yeah. We're entering a real new paradigm in the way that we'll be able to study these things, which is very exciting.
Also, the data sets themselves are some of the largest data sets we know physically how to make, and so that's very rich target for AI research. But also, the characterization data for the markup of that. Oh man, that'd be an exciting space to work on with some of the newer vector space algorithms combined with the computer or vision stuff. I mean, I'm sorry, I just even just breakthroughs of the last 3 or 4 years in AI combined with some of the newer sensors you have with astronomy. That's extremely exciting.
Yeah. Well, if anyone's interested in getting involved, please get in touch because we're going to have classification is going to become a really important part of pipelines for analyzing this data. It's definitely an exciting time. We're going to depend heavily, I think, on AI and machine learning techniques.
No, go ahead, Daniel.
Hi, Tim. How are you?
Hi, I'm well, Daniel. How are you?
Good. Yeah, I was just kind of talking in the chat a little bit, but I was waiting for you guys are having such an interesting conversation, and I'm really I'm definitely not like an astrophysicist. I do not have a PhD or anything, but I'm definitely a student of science, and I like to kind of like explore. I'm more of a curious mind, I guess you could say. So I have a couple of questions. If that's okay.
Yeah. Please go for it.
Sure. Some of them, one of them is on topic. 2 of them are kind of off topic. If that's okay. If not, you can disregard them, I guess. So the first one is I asked in the chat, like, is there a way to apply the golden ratio formula to white dwarfs in any way?
Not that I can think of off the top of my head.
There are ratios. They're just not exactly golden.
There you go. Could be silver or bronze. Yeah,
I don't know. Ultraviolet.
Yeah, there you go. Yeah, I don't know. Interesting question. I'll keep it in mind as I conduct my research.
Okay, cool. And then these ones are a little off topic, but if maybe you can help me with this. A friend of mine who also we call it a superpower, our bipolar 1 mental gifts that we have. But anyways, he came up with some interesting, fascinating thing. Now, if you shoot a beam of light onto the top of a pyramid into a black hole, what would happen?
Wait, so where's the pyramid?
Gaza in
The pyramid's on a black hole.
Egypt, and black. Oh, the black. I'm not. Good question. I don't know where the black hole is. It's kind of just very theoretical, but good question.
Yeah, I don't. Yeah, I don't know how that would differ from. I'm not sure what the pyramid is doing.
With the accretion race, the black hole would have even a small one. We wouldn't have Earth for very long. So, regardless of where you build it, we've got problems.
There you go. Any other questions?
Yeah, I had a question. So I read that you can also make assumptions about basically the parent planets from the real. So did you see any difference?
Difference in what?
Like, I don't know what the planets are made of, like different concentrations of something special about, something that
Yeah.
our system.
So from our X-ray observation, it's difficult. I mean, I showed the plot with the bulk Earth versus the photospheric abundances, and you can see we weren't very sensitive to differences there. And that's really because we're working with such small numbers of photons. So it's we're not really able to constrain different abundance models from this observation. Although I think that will be possible with X-ray observations in the future. But where we are able to do that is with the spectroscopic method, because we have like over 1,000 of these white dwarfs now observed like that, and there's a lot of amazing work that's happening through people studying both stellar evolution, but also exoplanet chemistries. And white dwarfs offer the only way to derive the bulk composition of an exoplanet. Probably exoplanet scientists would, not enjoy that statement and maybe disagree with it. But although in exoplanet science you have things like transmission spectroscopy, where you can derive or measure the abundance of an atmosphere on an exoplanet, actually being able to probe what is inside the exoplanet is very difficult. You can use the mass and the radius and a equation of state to derive internal densities and pressures and infer what materials you predict should be in there. But when these planets and planetary materials get ground down and rain onto the surface of the white dwarf, it's like kind of putting your planets and your moons and your asteroids into a blender, and then seeing all the constituent parts. So it's a really unique moment in planetary evolution. And it's the only moment that we can say, okay, like although the planet's been completely destroyed now, we know that it had this much magnesium, silicon, iron, aluminium, titanium, chromium. And the field has evolved to the point where we're able to say, okay, this white dwarf accreted something that was very crust rich or very mantle rich or core rich, or perhaps it created something, a chondritic asteroid. So we have detailed enough observations and numerous enough observations to be able to answer these kind of questions. And there's lots of work in the literature there. So if anyone's interested, feel free to contact me. I can send you more research that's been done on that. But where the X-ray observations come in is that they provide the first independent test of the models that are used in those studies. So it puts all of these studies on a really nice, solid foundation. I see, Katerina, you need to leave soon. Is that right?
Yeah, so I have to leave in 5 minutes. I'm really sorry, I can't hold.
That's okay. I also need to as well. So that's okay. Yeah.
Oh, yeah. So we planned for an hour, but I wasn't sure. Maybe there will be a few more questions. So I just wanted to give you a heads up. You could,
Okay.
But yeah, great. I think this was really interesting, and thank you everyone for coming and asking questions. Thank you, Chris, Daniel, Tuan, Dennis, Gilbert, Ryan, everyone, and of course a special thanks to you, Tim. This was a great discussion, and we learned a lot, at least me, for preparing for this, and also from hearing you speak. So, yeah, please come back anytime with updates or join our rooms. We'll have a few physics related rooms, but also other rooms. So, yeah, feel free to come back anytime or give us updates on your research. It's really interesting and amazing work. It's always fascinating what we don't do. So for me, it's more fascinating than my own job. So. Yeah.
Well, yeah, thank you so much for having me. It's been an honor to speak to you all, and yeah, thanks for the questions and for the invitation. You know, feel free to look me up. My email address is out there. I'll check Clubhouse as well. So if anyone has any follow-up questions or anything, you know, please feel free to reach out, and I'll get back to you.
Yeah, thank you. That's so nice. So thanks everyone. Follow the club if you like this type of rooms. We have guest speakers coming in. Sometimes we discuss. I have like round table of discussions about papers that just came out, and then based on how we discuss it, based on interest, we invite then the authors of the paper. So yeah, follow Science Society, and we will have our next room tomorrow. And I'm so sorry, I'm like doing breaking antimicrobial resistance by Dr. Mavridu. Scientists currently working on breaking bacterial antibiotic resistance, and she has done a lot of great progress. So she will share her work with us tomorrow. And then we have on the weekend suppressing genes across generations. Dr. Priyadishini will come, and then Dr. Lee from NIH will present his latest paper on mitochondria acting as microlenses in cone cells. And yeah, next week we'll have some more, but I'll update you next time because it gets a little bit overwhelming, the information. So thanks everyone. Enjoy the rest of your day, evening, morning, wherever you are around the world. And thank you again, Tim. It was a great honor. I hope you had fun.
I had a great time. Thank you so much for inviting me. Nice to meet you all.
You.
Thanks for joining us. Thanks for hosting us.
Thank you.
Thank you. Bye.
Bye.
3, 2, 1. Bye.